Hey everyone, this is Xingyu. Welcome to my channel. Today I'm going to tell you about optimization, and in particular a kind of optimization called linear optimization. But instead of tediously explaining what it is and why we care, I'm just going to jump straight into a problem. So here's the exciting problem. There once lived a girl named Bonnie, and she loves pizza. She loves pizza so much that she eats pizza every day for all of her meals for her whole life. Naturally, one day she decided to open up her own pizza store. However, the year's 2022. Bonnie had just suffered through 2 years of COVID, and now there's a recession coming and Bonnie's pizza business is just failing. So she had the great idea that you need to be unique in order to stand out. Therefore, she decided to not use the standard rectangular pizza boxes, but to use a box in the shape of a pentagon. The box looks something like this. But Bonnie has an issue. She doesn't know what's the largest pizza she can make that can actually fit inside this box. So our problem is to help Bonnie find the pizza with the largest area that can fit inside this weird pentagon box. Now let's stop and think how we can help Bonnie, because this is a serious question and her livelihood is at stake here. We essentially just need to figure out two things. The first is where the pizza should be centered, and the second is what should be the pizza's radius. Also, imagine this green circle is actually a pizza. It's not very clear where this pizza should be centered because we can place it anywhere inside the pentagon. And intuitively, for a fixed center, we want to choose the largest radius such that the pizza is still inside the pentagon. This is an example of an optimization problem. In optimization, we typically want to maximize or minimize a value, subject to some constraints. Here, we want to maximize the area of the pizza. Constraint is that the pizza is contained within the box. Now, let's try to translate all of this into math. We can let the variables u and v denote the x and y coordinates of the center. And we can let r denote the radius of the pizza. U, v, and r are called decision variables. These are the variables that we want to find. Now, the objective is just to maximize the area, which is pi r squared. Notice that we can equivalently just maximize r. The circle with the largest radius also has the largest area. The constraint is a bit harder to write. Try to convince yourself that for the pizza to be inside the pentagon, the center needs to be inside the pentagon, and the distance from the center to each of the lines containing the edges needs to be at least r. These distances are shown by the dashed red lines. In addition, the opposite is true. If these two conditions are met, then the pizza is inside the pentagon. Note a small subtlety here. We want the distance not from the center to an edge, but to the line containing the edge. Occasionally, this distance is different, as seen here. However, this doesn't matter. We could easily remove the words line containing, and they would still be valid constraints. But we leave it in because the math works out more nicely, as we will see later. But first, how do we calculate the distance from a point to a line anyway? Consider a point and a line. For convenience, let's label the point as Q and suppose it's centered at uv. And let's say the equation of the line is y equals mx plus b. The distance from Q to the line is the shortest distance from Q to any point on the line. This distance is precisely the length of the perpendicular line segment that passes through Q, which we will call d. Any other point on the line must have a larger distance to Q than d, because it forms the hypotenuse of this yellow triangle. So d must be the shortest distance. We can find d using some geometry and dot products. Let P be the point on the line directly below Q, so it has coordinates u, m times u plus b. From here, we can form the vector PQ. We can get the direction of PQ by subtracting the coordinates of P from Q. Now, let's choose n to be some vector perpendicular to the line. Since the line has a slope of m, for n to be perpendicular to the line, it must have a slope that's the negative reciprocal, or minus 1 over m. One potential choice for n is minus m1. Finally, let theta be the angle between PQ and n. Notice that the length of PQ times cosine theta is precisely the distance d that we want. We can multiply and divide by the length of n. As it turns out, the numerator is just the dot product between PQ and n. We can write out the vectors, and voila, using some algebra, we get the final expression. However, there's a small detail to notice. We need d to be positive, which means cosine theta needs to be positive, or theta needs to be in acute angle. This is true when PQ and n are pointing in the same half space of the line. If we choose n to be pointing in the opposite direction, then cosine theta and the dot product will be negative. Therefore, by carefully choosing the orientation of n, the sign of the dot product lets us know which side of the line Q lies on. This can be used to ensure the center lies inside the pentagon. Alright, let's go back and use our new profound knowledge to derive our constraints. Recall the two conditions we had before for a pizza to be inside the pentagon. Again, let's let the center of the pizza be Q. And let's take a line containing one of the edges. We can calculate the equation of this line, which in this case is y equals minus x plus 8. From here, we take a point P on a line. Any point will do. In this case, P equals 6, 2. Now, we can form the vector PQ. We need to choose a normal vector n. Remember that the dot product between PQ and n is positive if they point in the same half space of the line. We can choose n to be pointing inside the pentagon, and then force the dot product to be positive. If we do this for all of the edges, then this will ensure that Q lies inside the pentagon. Now, let's calculate the dot product. PQ is equal to u minus 6, v minus 2. There are many possible choices for n. We just want the slope to be 1 because the line has a slope of minus 1, and we want it to point inside the pentagon. An easy choice is setting it to minus 1, minus 1. Now we can simplify it. From here, we just require this value to be greater than or equal to the radius r. If this constraint is satisfied, then the center will be at least a distance r away from the red edge. We can similarly calculate a constraint for each of the remaining edges in the same way. Finally, we need a constraint that the radius r is non-negative. This also forces all of the dot products to be positive, which will make Q lie inside the pentagon. If our choice of u, v, and r satisfy these constraints, then our pizza will be inside the pentagon. Let's do a sanity check that our constraints do work. The coordinates and the radius of the green circle are displayed here. The values of the constraints are displayed here. If it's green, it means the constraint is satisfied and the value is non-negative. Otherwise, it's red. Let's check these constraints for various circles. Alright, it seems like the constraints are working as expected. If the circle is not in the pentagon, then at least one of the constraints is violated. Now, let's write our optimization problem in its entirety. Our objective is to maximize the radius of the pizza. Next, we write our distance constraints as well as the constraint that the radius is non-negative. We can rewrite these constraints by moving all of the variables to one side. This final form is called a linear program. In a linear program, the objective function and the constraints are all linear functions of our decision variables, which are colored in red here. Also, although here we only have greater than or equal to constraints, we can also have less than or equal to and equality constraints in a linear program. Okay, you may be thinking, once we formulate a problem as a linear program, what do we do next? There are lots of algorithms that have been developed that can handle large-scale linear programs, for example, with millions of variables and constraints. The most famous such algorithm is called the simplex method. We won't cover any of them in this video, but I will give some geometric intuition on how to find the optimal solution. To get some intuition, let's try plotting these constraints. The vertical axis is for the r variable, and the left and right axes are for the u and v variables. Let's first plot the constraint v minus r is greater than or equal to 0. The equation v minus r equals 0 defines a plane. Now all of the points that satisfy the constraint lie on one side of the plane. In this case, it's below the plane. We can plot the remaining constraints the same way, one by one. Let's plot the next constraint. As before, we first plot the plane. All of the points that satisfy this constraint lie below the plane. This gives us a new feasible region. The points in this region satisfy the first and the second constraint. Now, we just keep continuing with all of the constraints. Okay, this is the final feasible region. The points in this region satisfy all of the constraints. We just need to find the point with the largest radius. This is the point with the largest R value, and it's indicated as the red point on the polytope. This optimal point has a U value of 3, and a V and R value of approximately 2.071. Now, let's take the optimal point that we just found and see how large of a pizza Bonnie can make. We want the pizza to be centered at U equals 3, V equals 2.07 with a radius of 2.07. Voila, so this is the pizza with the largest area that fits inside this pentagon. I hope this problem demonstrates what a linear program is and also how useful it is. It wasn't so obvious that this problem could even be written as a linear program in the first place. One area that I glossed over was how did we actually come up with the optimal solution. In the next video, I'll talk about solving linear programs in 2 dimensions. Let me know in the comments section what other interesting problems can be formulated as a linear program. And if you liked this video, please support the channel by clicking the like button. Thanks for watching.